Hello Year 12 and welcome to our first video here for our new topic, graphs and equations. Now many of these ideas we're going to be revisiting after having done them as part of the extension course in Year 11. But let's go back over some of these things. An interval is going to be a range of values on a number line. Now we can have an open or a closed interval depending on whether or not we include the endpoints. And I can have an array if I have an endpoint and everything either greater than or less than that point. We've got our bracket interval notation, which we've used before. We use a round bracket to indicate an open interval, okay, where we don't include that point. Graphically, we're going to represent that with an open circle, and symbolically, we're going to use a strictly greater than or strictly less than symbol there. For a closed interval, I use square brackets. Graphically, I'm going to have like a coloured in circle on the end of my interval array. And symbolically, we're going to use greater than or equal to, or less than or equal to. There's a table here to fill out. Let's have a look. Now I have here a closed interval from from 1/3 to 3, right? Because they're closed intervals, I use the greater than or equal to symbols, and using my bracket interval notation, right? The square bracket indicates closed interval and equal to that point, and I put the 1/3 and the 3, right? Either end of that interval with a square bracket on both sides. Next up, we have an open interval from -1 to 5. Open because we have this open circle here on our diagram, and a strictly greater than symbol showing that x is between -1 and 5, but not including -1 or 5. Using our bracket interval notation, this time we have to use round brackets. So my round bracket, -1, 5. Okay. You can see here the bracket interval notation, particularly for open intervals, can be a little ambiguous, could easily be confused with a coordinate, with perhaps a point on a number plane, but it's very different to that. Okay. We have to be clear when we are using that sort of notation that it is an interval we're referring to, not a point on a number plane. Now this is neither an open nor a closed interval because I'm going to include -2 but not 3 and all of the values in between. So neither open nor closed. -2 is our lowest value and x is both greater than or equal to that, but it must be less than, right? X will be less than 3, or 3 is strictly greater than x. Okay, so we write it like that, and you see here our bracket interval notation uses a combination of square and round brackets. Here we have array, so this represents all of the values greater than and including -5. Okay, so we should be quite familiar with our inequality, our symbolic representation here, and that's going to be x is greater than or equal to -5. Our bracket interval notation now, right, I need something to sort of finish it off. I've got a square bracket to begin with and -5 because that's our lowest value and it includes that value. But then it goes on forever, so we put an infinity symbol there with an open bracket there because it's not going to actually include infinity, just heads off in that direction. Okay. So getting a little further along now, I have an open ray, which means we have an open circle at the end, from 2 to the left, right? So that means x is strictly less than 2. Okay. So we're going to draw it like this, right? Start off with our number line, x, my point 2 here. Now, it's not going to include 2, so an open circle and everything to the left of that, or everything less than 2. There we go. That's our diagram and our bracket interval notation. Right. Negative infinity here on the left. And a 2 on the right. And it doesn't include 2, so a round bracket again. Now, I don't have any of the things here. A closed ray from 2 to the left or the open interval from 3 to 4. Okay, I've got a few things here. Right, better put my little axis here, x. Now, closed ray from 2 to the left. I need a 2, a 3, and a 4 here. Now, it's a closed ray to the left. So, closed circle, and an open interval from 3 to 4. Open circles here, 3 to 4. That's our diagram. Now, as an equation here, I'm going to say that, let's say 2 is greater than x. Or I could say x is less than 2. I want that, or I'm going to use a union symbol. Or x is between 3 and 4. It doesn't include 3 or 4, so x is greater than 3 and less than 4, like that. I can write it like that. I could put an or in there instead of the union. That'd be okay as well. But I'm using that union symbol, and I'm going to do the same with our bracket interval notation. So, the first thing I have is negative infinity. Up to 2. And including 2, so a square bracket. Put my union symbol again, and then I have not including 3, so a round bracket 3 to 4, and a round bracket again. Okay, that's representing intervals and rays using a variety of methods. Rightio. Now, a little bit of stuff here again on composite functions. We've certainly spoken about this before, but haven't quite exactly used this notation. So we've talked about the f of x, right, the function of x, and I can substitute values into that function. So if I want to find the function of 3, I replace x with 3 and evaluate it. I can do a function of a function. So I could have the function of function x, or the g of f of x, or the f of g of x, and a variety of these things. Now, instead of putting brackets around brackets, we can use this little, I suppose like a tiny little O that sits in the middle of the line. Now, I've got two functions here, x plus 3 and x squared. The g of the f of 5. Now, the f of 5 will be 5 plus 3. Okay. So I've got 5 plus 3, but the g of that means squared. So I've got 5 plus 3, and then that is squared, right, which is 64. B here, I've got the reverse. I've got the f of the g of 5. Okay, and this is not necessarily the same thing. So the g of 5 is 5 squared. Now to do the f of that, I have to take that and add 3. So this time I get 28, right? Altogether different. Now the g of 5 will be 5 squared squared, which is 25 squared, which is 625. And the f of x, right, is x plus 3, which is x plus 6. Okay, composite functions, nothing terribly new there, slightly different notation. Let's talk a little bit about the sign of a function. By that I mean positive or negative. So some functions might always be positive, something like y equals x squared plus 1. That function is always positive. A function like y equals negative 1 minus x squared, or negative x squared minus 1, that's always negative. If I had a function like y equals x squared minus 1 it would sometimes be positive and sometimes be negative. We just want to see when this might occur. One of the ways we can do this is to find the sort of critical important points on that function. And we have techniques for finding those. Now, I can't go from being positive to negative without one of two or maybe three things occurring. I either have to be 0 at some stage and cross the x-axis, or I might have an asymptote and a break in the function, such as a function like y equals 1 over x. Right? Y equals 1 over x. If x is, say, negative 1, then my function is negative, the sign is negative. If x equals 1, my function is positive. My function is undefined at 0. Somehow it gets from negative to positive. It changes sign, but it's never equal to 0. And that's because I have an asymptote with a discontinuity. It's also possible sometimes to have a discontinuity that isn't an asymptote. Right? For example, if I have y equals x plus 1 squared over x plus 1, right, we might think we can cancel a common factor of x plus 1 from the numerator and denominator and just have the function y equals x plus 1. However, right, that might be a useful approach for many things. We have to keep in mind the domain doesn't include negative 1, because in my original function, x plus 1 all squared over x plus 1, my denominator would be negative 1 plus 1 would be 0, and I can't divide by 0. That includes when I am simplifying an expression. Right? I can't cancel a factor of 0 from the numerator and denominator. I can't divide by 0. Now, as long as x doesn't equal negative 1, as long as my denominator isn't 0, right, I can still take that approach to determine what's going on, but we have to keep in mind I have a discontinuity, and most of these are going to occur when my denominator is equal to 0. So, we are looking for any zeros of our function, anywhere the function is 0, right? Anywhere where y equals 0, okay, our x-intercepts. So I'm looking for those. I'm also looking for any asymptotes or discontinuities. Now, I have this inequality here. 3 over 2 to the x minus 1 is less than or equal to 1. So, let's consider this. Is there any way... actually, it's much easier if we have this equal to 0 or relative to 0. So let's change this around a little bit, and I'm going to say that 3 over 2 to the x minus 1 is less than or equal to 0. Rightio. So now I'm chasing the sign of this thing. I don't want to know where it's less than or equal to 1. I want to know where it's less than or equal to 0. So really I want to know where it's positive and negative. So let's consider the domain of this function first. Are there any values that x can't adopt here? Well, I can't have a denominator of 0. And if x was 0, I would have 2 to the 0 minus 1, 2 to the 0 equals 1. 1 minus 1 would give us a denominator of 0. So we have to recognise that x can't equal 0. Now, is it possible for this to be equal to 0 anywhere? Right? Is it going to touch the x-axis? Well, if 3 over 2 to the x minus 1 was equal to 1, then it would be equal to 0. And that would mean that this term here, right, the first term there, the 3 over 2 to the x minus 1 would have to be equal to 1. That would mean my denominator would have to be equal to 1. That would mean that 2 to the power of x minus 1 would have to equal 3. Mean 2 to the power of x would have to equal 4, which means x equals 2. So, if x equals 2, 3 over 2 to the x minus 1 is less than, is not less than or equal to, is equal to 0. So the points I need to look at, when x equals 0 and x equals 2, I'm going to say x and the sign of my expression, the left-hand side here. So I need to check what happens when x equals 0 and when x equals 2, and what I also want to do and always want to do here is have a look at what happens on either side. So I need to choose a number that's less than 0. I don't know, let's say negative 1. Doesn't have to be negative 1, but negative 1 is definitely less than 0. Number between 0 and 2, 1 seems like a good choice there. And a number that's greater than 2, let's say 3. If I chose 5 or 10 or 97.5, that would all be fine. Right, I'm only interested in the sign, and the sign can't change anywhere greater than 2. Right? Whatever the sign is for something greater than 2, it will have the same sign for every value greater than 2. All of the values between 0 and 2 are going to have the same sign. All of the values less than 0, right, for every value of x less than 0, they will all have the same sign. Right. So now, let's investigate what's going on here. Double line here. Okay, there's a pretty scrappy looking table. Now, when x equals 0, what do we get? 3 over 2 to the 0 minus 1. I've got a problem. I'm just going to put an asterisk here and say undefined is what that's going to represent. What if x is negative 1? So, 2 to the power of negative 1 is a half. Half minus 1 is negative half. 3 divided by negative half, well, it's positive divided by negative is negative. That's all I care about. Is it positive or negative? So for any value of x that is less than 0, this expression will be negative. Now, let's see what happens when x equals 1. 2 to the 1 is 2 minus 1 is 1. 3 over 1 is positive. 1 minus... hang on. Oh, I think something's gone wrong. 2 minus 1 is 1. 3 over 1 is 3. 3 minus 1 is 2, which is definitely a positive number. Now, if x equals 2, 2 to the 2 is 4. 4 minus 1 is 3. 3 over 3 is 1. 1 minus 1 is 0. Neither positive nor negative when x equals 2. And finally, 2 to 3 is 8. 8 minus 1 is 7. 3 over 7 is positive. I should check here a little bit. 3 over 7. What did I say? 3 over 7 is less than 1. That'll do us. Minus 1 makes that negative. Okay. So, to find where this expression here is true, where 3 over 2 to the x minus 1 is less than or equal to 1, well, it's when x is not equal to, so x is strictly less than 0, or x is greater than or equal to 2. Right. In bracket interval notation, negative infinity to 0, and not including 0, we'll put the little union symbol here, and square bracket, because we're going to include 2, up to infinity, and a round bracket there. So, we have solved that inequality there using a table of signs. It's not the only way to do it, and I would suggest it's probably a bit of an awkward way to do it many times, because we have to find those zeros, and there's a little bit of fiddling around doing that It is a fiddly process. However, sometimes our other methods fall apart, and we have to fall back on this one. You just got to test a whole lot of things. Remember that we can't change sign without either some sort of asymptotal discontinuity or by crossing the x-axis. And if neither of those things happen, then the sign won't change. Rightio. I'm pretty sure that's it. Okay, there is a bit of a rundown there. We haven't probably done those solving inequalities using a table of signs. A few little interesting new bits of notation, but generally speaking, I think we have covered a fair bit there. If you've got any questions, make sure you ask me. See you in class.